We want to have a little discussion about concrete behavior. Let's have a look at a stress-strain diagram of the concrete, which is very important to understand. As you can see, there are three curves have been shown here for three different levels of F'(C) or concrete strain, which is 25 MPa, the other one is 50 MPa, and the third one is 100 MPa. As you can see, these curves are a little different. For 25 MPa, the ultimate strain is happening somewhere here. And then after that, there's a long way until the concrete crashes at the end. For 50 MPa, the ultimate strain is happening in a higher level of strain. And then after that, concrete is going to lose its strength and it's going to fail at the end. 100 MPa has an interesting curve. As you can see, the maximum, the ultimate strain is happening in a very high level of strain. And then after that, we're going to have sudden failure. So as you can see, concrete has a very different behavior when with different levels of F'(C). And when you're choosing a value for your design, you need to be aware of these differences. Also, the slope of the line in the beginning of the curve, which is kind of linear. So this is for 25 MPa, and this is for 50 or 100 MPa. It's called secant modulus of elasticity, and it's used to calculate short-term deflections. In the working range load, the concrete may reach the stress of approximately half F'(C), and in this range, the stress-strain diagram is approximated by a straight line. So we're going to use this as a fact in our analysis in the next few sections. Also, the strain at ultimate stress or crushing of the concrete is about 0.003. And this value is really important. We need to keep this value in mind because we're going to use this value a lot when we are analyzing our section for plastic behavior. We want to understand the behavior of a reinforced concrete section and the reason why we use a steel reinforcement. Let's have a look at two examples of beam. The first one is plain concrete, which is shown here. And the second one is a RC concrete beam or reinforced concrete beam. In the plain concrete beam example, we are having a point load applied in the middle of a simply supported beam. So the bending moment diagram for this beam is going to look like this. So we are having the maximum bending moment in the middle, which is going to put the area under the neutral axis, which is shown here, under tension, and the area above the neutral axis is going to be under compression. So tension capacity of the concrete is very low, and if this tension applied is higher than the tension capacity of the beam, we're going to have big cracks, especially in the middle that we have the maximum bending moment. As a result of this crack, concrete is going to fail, and this failure can be a very sudden failure. Now, to avoid this failure, if we add a steel reinforcement to the bottom of this beam as shown here, instead of having a big crack in the middle, we're going to have a small cracks developing along the length of this beam. And also the tension will be transferred to this steel reinforcement. And as a result of that, the ultimate capacity of this beam is going to be much higher. Also, if you want to know how does the stress-strain diagram look like for the steel, you can look at this picture here. As you can see, the diagram looks very simple. It just has two different parts. And as you can see, it's a lot more predictable than what you have seen for the concrete, because the steel is a lot more predictable material than the concrete.